All right. Hello, everyone. And happy spring. I won't take it personally that so many people are gone and out there enjoying spring, I hope. But I'm going to get, so we last time covered confidence intervals and did not get to the T distribution. I'm going to start this class by going over the survey that about half of you did, and then go back to the T distribution. And I don't know what you think about this, Tony, and how this meshes with your plans, but I'm not even sure about getting to hypothesis testing today. Kind of see how it goes, but if all we do is review confidence intervals and introduce the T distribution today, it'll be okay. And then we'll be a full class behind, then I'll just update the syllabus. We'll see how it goes, but feel free to ask questions. If you ask questions and take up time, we'll be more likely to spend more time on the thing that we're working on. All right. So, just curious, how many of you filled out the survey and made guesses about my age? Did anyone forget to do it? Just one? Just two? All right, well, about half of you did, so if it's more than half in this class, then maybe your being here is like correlated, statistically associated with being a more active participant in general. I don't know. But I took the responses you gave. It was in a Google form, and Google Forms allows you to just download the results in a spreadsheet as an Excel spreadsheet or a CSV file. I did it as a CSV file, and I read them using R. Did some kind of ugly stuff to them. I did, well, I did some t-tests just I used this function actually just to calculate the confidence intervals to avoid doing it manually. This is an automatic way you can do it in R. And then I plotted them. So I wanted to take a look and see exactly, let's see if I can make this full screen and a little bit bigger to see exactly what kind of guesses all of you made. This is pretty interesting to me, both because it's my age and because I get to see what all of you think about confidence intervals. So let me see, I'm gonna look at some of these. They're sorted here from top to bottom by order of, I believe it's your point guess, although actually there's a little bit of variation there. So I can't quite, I'm not actually sure quite how these are sorted. Maybe they're just in order, but well, I can take a look. The code is right here. What did I do? By the third column, although I'm not sure right now what the third column is. Whatever the third column is, I think it's the point estimate. They're supposed to be sorted by that. So what I did, these circles here are your best guesses. The red lines are your 50% confidence intervals, and the black line is your 95% confidence interval. So let's just take a look at this top one here. This person's point estimate for my age is 63 years old. That's interesting. Don't worry, you don't have to tell me they're anonymous. That's why I make them anonymous, so you can guess freely. So point estimate guess of 63 years old. I'm guessing this is a very young person because to young people, everyone older looks really old. And the 50% confidence interval goes from 60 years up to about 70 years. And the 95% confidence interval starts in the same place, which is kind of a little unusual, and goes up to about 75 years old. I don't know if I'm going to be teaching here when I'm 75 years old. But I don't know, any comments about this? Is there anything that strikes you as unusual about these confidence intervals? Besides it being a very high guess, we'll overlook that. That would be under what we would call a bias. There's like, that's a systematic error from my true age. But can someone tell me anything unusual about these confidence intervals? Yeah?
To be equally distributed, so 90% and 50%. So, quite skewed, but like the 50 and the 95 on the left side are the same.
Right. So yeah, that's the first thing that I noticed about it, is that the left-hand sides are the same. So whether you're 50% confident or 95% confident, that the lower bound is 60 in both cases. And maybe you can think of some instances where that would be the case, that like all of the additional uncertainty happens at the upper end of your confidence interval, but it would be pretty unusual. Something like that maybe would happen if, like, you know, you knew about some life event of mine, and you knew that I cannot be less than 60 years old. So all of your uncertainty is at the upper end of the spectrum. There's no uncertainty at the lower end. In that case, that could happen. But unless there's some reason that you know I'm more than 60 years old, probably those intervals should differ on both sides, because there's uncertainty above and below your point estimate. These next three, these all look like pretty reasonable confidence intervals. To me, they're pretty much as expected, in that the point estimate is in the middle of the intervals or close to it. The 95% confidence interval is wider than the 50% confidence interval. So if you want to be more confident, you have a wider confidence interval. That all makes sense. This one's a little unusual because the 50% confidence interval, the upper limit is the same as my age. So they're guessing that I'm, I don't know, 42 years old, but they're 50% confident that I'm either 40 or 41, not above 41. So that's a little unusual. Here's another one like that, that the upper limit of one of the confidence intervals is at the point estimate. So that's always a little bit unusual, because it means that all of the 50% of uncertainty is below, none above. So it's like they're quite confident, at least at the 50% level, that I'm not more than 41 years old. But there's some uncertainty with how much less than that I might be. So let's see. Okay, the next one that's really surprising maybe is this one. Can anyone tell me what's unusual about this set of intervals?
50% confidence level is greater than the 95%.
Yeah, very good. So this one is highly suspect, because the 50% confidence interval is greater than the 95% confidence interval. That doesn't make any sense, right? Because if you're going to bet even money with someone that I my age is within a certain interval versus you're going to give them like 20-1 or 19-1 odds, you're going to want to give a bigger interval if you're going to have to pay out like $100 to their, what would that be, to their $4. So there are a couple of them like that. It's not too bad though. Here's another unusual, very unusual one, that the 50% confidence interval doesn't include the point estimate at all. That never happens because your confidence region should include the best guess. It doesn't make any sense otherwise. Usually that best guess is right in the middle of the confidence interval, but in any case, it has to be somewhere within the confidence interval. And one more, this one might be a mistake. I don't know. There seems to be no spread in the confidence intervals. So, anyone still? Did any of you who might have put one of these ones that we talked about understand the error of your ways? So if you're going to guess my age, you just give it a number. Your best guess. That is the point estimate. That is your best single guess. But it doesn't say anything about how confident you are in that guess. To say something about your level of confidence, you have to give an interval. And you can give an interval that represents how much uncertainty you have around that guess. And if you are going to be 50% confident in an interval, that's not too confident. You can still give a pretty small interval. You're going to be 95% confident. It needs to be a bigger interval, a bigger range of guesses, right? Because you really don't want to lose your bet if you're giving, 20-1 odds on it. If it's a 99% confidence interval, you have to be really certain, and it has to be a bigger interval. Maybe to be 99% sure, you want to guess all the way from like 30 years old to 80 years old, right? And to be 100% confident, well, that has to cover every single possible value. So the more confidence, so the higher confidence level, the bigger your interval, and good confidence intervals, it doesn't mean that you're more confident in it. It just means that they accurately represent your uncertainty. So, your confidence level, or your a 50% confidence interval is not any better or worse than a 95% confidence interval. You're just representing a different level of uncertainty. And different confidence levels have different purposes. And as long as you have an unbiased and accurate representation of your uncertainty, then it's a good confidence interval. Now, these confidence intervals are just based on your guesses. They're not based on any statistical test. This up here is actually based on a statistical test. What I did was I took all of your point guesses, not the intervals, just the guesses, and I used the t-distribution, which we're going to use after this, to construct a 50% confidence interval and a 95% confidence interval around your guesses. And those are based on the assumption that your point guesses are a random sample from some larger population of similar students. Whatever that population may be, I'm just assuming that each of your guesses are independent, that you weren't discussing it with each other and putting in a guess together, that you made independent guesses, and that you're somehow a representative sample of some larger population. So my interpretation of this point estimate would be this is the average age that students think I am. So it's really an estimate of just your point, or the average point estimate guess given by some large population of students of which you are representative. And that comes out to, what is it, about 42, 43 years old. And the 50% confidence interval is quite small, and the 95% confidence interval is quite small. But how would you interpret these confidence intervals? They're a little bit different than what I asked you for. Who wants to tell me how you would interpret this 95% confidence interval, which is the black line? Anyone? What's the interpretation of that confidence interval?
For the black line and 95% confident,
Yeah.
you were between, looks like to me, between 40 and 40.
Let's say it's between 40 and 44. What's the interpretation of that 95% confidence interval? I think you have a good idea. What's that? Yeah. So I think, so what you said was that 95% of the time people are going to guess that my age is within that interval.
Yeah.
That's not quite it, because what you're talking about are individual guesses. And you can see from these that 95% of these guesses don't fall within this. This is only 17 guesses, so if only one of them falls outside of that guess, that would be about what you expect. But it looks like 2, 3, I don't know, at least 3 of the guesses fall outside of there. So, and remember, confidence intervals are not about individuals. They're not about individual observations or individuals from the population. They're about averages. So it's not an interval that we expect to contain 95% of all of the guesses. What is it? What does it contain 95% of? Yeah?
The average, yes.
The
Average of the 95% of the average.
Yeah, you're getting there, and statistically that's correct. It's not the most sort of intuitive explanation of that. If we repeated this a large number of times and calculated the average guess for each one, 95% of them would fall within this interval. That's true. But there's a more intuitive interpretation of this in terms of like the population average of the guess of my age. So if we took the population of students of which you're representative, let's say that's all graduate students at CUNY, they're going to have, and we're to give this to all of them if they all knew me, and calculate their average guess. That is the population average estimate of my age. How do you interpret this 95% confidence interval in terms of that population average? Yeah.
So is it unitless? So we just supposed to say there's a 95% possibility that the age that was guessed fall to the parameter.
So again, it's not 95% of the guesses that fall within this interval, because it's not about individual guesses. Yeah.
But the confidence interval gives you a range, right?
Yeah, confidence interval gives you a range.
So I'm interpreting your question as you're asking us what the 95% is measuring, right?
Yeah.
So if it's not measuring the total conclusion of the number of attempts to guess your age, then what is it measuring?
Yeah.
Like if it's not based on population, right?
It comes from a sample,
Okay.
this interval. It comes from the sample that is my survey of the class. But that confidence interval does represent something about the population. It's representing an inference about the population.
So does it represent that particular sample? Because you can run them over and over again, right? You can ask other classes, you might not get the same confidence.
Right? Yeah, if I asked other classes, I wouldn't get the same confidence interval. But it's an inference about the population. We're using one sample to make an inference about a population. What is the population parameter that we're making inference about here? It's something that if I could ask every student that I've ever had, let's say that's what the population is, if I could ask them all of this week and get their answers, there's some attribute of that population data that we're making inference about. What is it?
Teachers and students.
No, just me. It's a very self-centered survey here. No, the population is a population of many students, all being asked the same question.
The question is, what's your age? And
Yeah.
That's the point estimate. That's the sample.
Yeah, so the question is, what's my age? And the point estimate is what? Did you say? Yeah.
We're using the example to reflect back to the population. So
Yeah.
is it saying that like what we get, the 95 benefits, then what they get, like I don't know.
Plus or minus 2 standard deviations.
Yeah, I mean, that's mechanically what it is. In my experience, it's way easier to teach students how to calculate a confidence interval than it is how to interpret it, which is why I'm kind of focusing on how to interpret it here. How to do it, you'll do that in lab. You'll be able to do these no problem. But what does it mean? And I can see we're not quite there yet about what it means. So I'm going to go and review a little bit from yesterday or last week. let's see. So here's the example that we talked about last week. Given a random sample of 309 infants with a sample mean birth weight of 119.6 ounces and a standard deviation of 18.2 ounces, what is the average birth weight of infants in the population, and what is the 95% confidence interval on the average birth weight? So we only had a sample of 309 infants, but we want to make an estimate about the average birth weight in the population and have some estimate of the uncertainty in that average, because we have a finite sample and there's some random sampling error involved in taking a sample of selecting 309 infants out of this entire population. And that was not, I tried to highlight the interval containing the birth weight of 95% of all infants. So it's not about the birth weight of individual infants, but it is about confidence around the average birth weight. So we did this by taking the point estimate, calculating the margin of error, which is the uncertainty above or below the point estimate. The point estimate was the mean of the sample data. This margin of error was uncertainty above or below that point estimate. Yep.
So the 95% confidence interval,
Yep.
Does it have to do with the mean?
Mm-hmm.
Since there's many samples, the mean would always be within the same range, correct?
What do you mean? What do you mean?
Like,
The mean of what?
I don't know if I'm explaining this correctly. Like, if you're running this sample and you're doing it multiple times, right?
Like this?
Yeah, I guess.
Yeah, if you're repeating your experiment.
Right. So the 95% confidence interval means that the mean of all these studies that we ran would fall within that range.
No, that's not an interpretation of the confidence interval. This is one interpretation of the confidence interval. In this example here, it's a simulation, so I know what the population average is, if this is the population average infant birth weight. These are confidence intervals constructed each from a single sample, and I'm repeating this 100 times, I think, here. Or maybe it's, yeah. And calculating a confidence interval each time. And what I see here is that maybe these are just 90% confidence intervals, because it looks like about 9 out of 10 of these confidence intervals contain the correct population mean. So this population mean is fixed, it's set, but it's unknown. What we have is just a single sample drawn from the population, and we have an average estimated from this little sample, and we're drawing a confidence interval around the mean of that sample that should contain the population average 95 times out of 100 for a 5% or for a 95% confidence interval. So if we were to do our little experiment many, many times, about 95% of the time, that interval would contain the correct population average. Yep.
So is that assuming that that it's not skewed and that the sample is higher than 30? Are we always going to assume that?
We don't have to assume the sample is larger than 30. The methods can be a little bit different if the sample is larger than 30, but we do assume that there's no bias in the estimate. This confidence interval accounts only for sampling error. It doesn't account for bias. So if you have a broken scale that always reads 10 ounces too much, it's not going to account for that. And you're no longer going to contain the correct population average infant birth weight 95% of the time with your 95% confidence interval.
So just to clarify, we're taking the population, we take a sample of that, and then we take the mean of that sample, and then we assume that the mean of that sample is equivalent to the population.
No, we do not assume that the mean of the sample is equivalent to the mean of the population. We know it's not because it has sampling error. We do assume that it's an unbiased estimate of the population average, and that was contained in that first part of the central limit theorem, that the mean of the sampling distribution is equal to the mean of the population distribution. So we have this 1 point estimate. We assume it's an unbiased estimate of the population mean. But the only way we can have an idea of how close it is to the population mean is by constructing a confidence interval. It tells us how much we expect the sample mean is probably different from the population mean, and it tells us how confident we can be about where the true population mean is, even though we're never going to get to observe it directly. So in this example, this shows us the situation that we can never do in real life of repeating our survey over and over again and seeing how each time we get a different sample mean, we get different standard deviations resulting in different widths of the confidence interval, so it moves left and right, it gets larger and smaller. But regardless, 95% of the time, that interval will contain the true mean, and that true mean never changes. That is, it's one population that we're drawing repeated samples from that give us a sampling distribution of averages. I think you got all of these right last week. I guess I could ask you again. Is a 99% confidence interval larger or smaller than a 95% confidence interval? Larger, very good. As the size of a confidence interval increases, does the confidence increase or decrease? It increases, you said? Yeah, it increases. As your sample size, N, increases, does the 95% confidence interval get bigger or smaller? Smaller? You guys are doing great. And what does the confidence interval tell us about variability of individuals in the population? Well, you're not as confident about this one. Nothing. No, it's not about individuals. It's not about individual birth weights. It's not about individual guesses about my age. It's about confidence that the true population average falls in this range. So let me ask you this again. This 95% confidence interval that I calculated from all of your point guesses, it goes from, let's say, 40 to 44. How can you interpret that?
I'm 95% confident that you
between 40 and 44. 40 years old and 44.
Yeah, that's a pretty good interpretation. So it says, well, if your guesses were unbiased, if we knew that your guesses were unbiased, that on average people thought I looked my age, then it would tell you that you could be 95% confident that I'm between 40 and 44 years old. Since we can't be sure that your guesses are unbiased, and I might look more or less than my age, then we probably have to interpret it as this is what the average student thinks my age is. So it's like the average guess for my age among all of the students lies somewhere between 40 and 44, just that point average, the average of everyone's guess. Which, as it happens, is wrong. I'm not between 40 and 44 years old. I'm 45 years old. So that's a good lesson in that if there is a bias in the guesses, then I mean, it's always possible that the true population average is outside of the 95% confidence interval. That would happen 5% of the time. But if there's a bias involved, either, let's say, because lots of students talked together and made the same guesses, so they're not independent, or because I look a little bit younger than I am, then this interval is no longer going to contain the correct population average 95% of the time. So you can bet I'm good, after spending this much time on confidence intervals and their interpretation, that I'm going to try to check to make sure you understand what they mean. Besides just the mathematical calculations of them, but also that you can interpret them correctly.
Can you repeat just if there's bias, like what happened?
Yeah, so confidence intervals, one of the assumptions of them is that the measurements that we have are unbiased. They're unbiased both in that they're a random sample from the population, and there isn't systematic measurement error in them. So if either you are not a representative sample of the population of students, or you tend to systematically underguess, either of those things can cause the 95% confidence interval to be less than 95% sure of containing my true age. Any questions? So does one person want to give me now in their own words how to interpret, let's say, this little 50% confidence interval that's only about plus or minus 6 months? How would you interpret that? This is your chance to make sure that you understand that correctly and have me tell you yes or no and correct anything you say that isn't right. So you should be jumping at the opportunity. Yeah.
It's that 50% of the time, the average is contained in that number of the guesses of the population, the average of the population. We are confident 50% of the time.
Yeah, very close. Although I would say just be very clear that that population error, that population average number doesn't change. So it's not that 50% of the time it falls within this interval. If we repeat the study, this interval is going to move around, but 50% of the time, our little survey that its 50% interval will contain the correct average.
50% of the time, the confidence interval is going to contain the correct average, no matter what who takes the survey.
Right. So if we consider that average of like all CUNY students answering this question, that's a single number. And we're about 50% sure that it's between like 41.5 and 42.5 years. And we're about 95% confident that that average guess is between 41 and 44, something like that.
So we're 95% sure that it's always going to be between.
Well, again, when you say always between, keep in mind that this particular interval changes with every survey you do. So the survey, the sample that you take, and the interval you calculate is ephemeral. You can repeat this survey for the rest of your life, and you'll never get exactly the same confidence interval.
But that's why I'm a little confused, because you're saying don't say that it's 50% sure that these guesses are right.
I'm 50% sure that the average of the guesses of every student, there's that one true population average guess. So if I ask all 400,000 students what age they think it is and calculate that average, so that's just one very precise number. I'm 50% sure that that number is between 41.5 and 40.
Based on this small sample, you're 50% sure if you extrapolated the population.
Yeah, that average would still fall within here. So think about that. I mean, this is only 17 students. As long as it's a well-designed sample so that it's representative of the population and it's a proper random sample, I don't have to go ask 400,000 students. I can just ask 17 and say that average is, I'm 95% sure it's in this range. And so, you gain a lot, and you make it possible to know quite a bit about this population average value just from this small sample, 17 students. That's what's so powerful about samples, is that it doesn't matter how big that population is. That could be the population of New York, 8.5 million people. But when when the New York City Haynes examination goes out and collects a random sample, they don't need to ask 8.5 million people. They just ask 1,500 people and infer about the entire population from that. And if they want to say something about what the prevalence of diabetes is from that sample, they don't need a registry of every diabetes patient. Or if they want to know how many, what fraction of the population of New York smokes, they don't have to somehow interrogate every single person in New York. They only need to interrogate 1,500 people, and then they can tell you, I don't know, 20% of the population of New York smokes. 95% confidence interval is between 17% and 23%, or 95% confident that the true proportion of smokers in New York is between 17 and 23%, just from this one sample. And as long as it's a statistically random sample and it's not biased, then you can have that 95% confidence. So does that kind of sink in a little bit about how powerful that is? That you can not only get like an average guess and not just something about the people who answered this question, but I can make this inference about a huge population and say how much confidence I have in that inference from this small sample. One more little calculation that I did. The ratio of the width of the 95% confidence interval to the 50% confidence interval, assuming a t-distributed sampling distribution, the ratio would be about 3. So the 95% confidence interval would be about 3 times bigger. Yep.
So I have a question about the percentage of confidence interval.
Yep.
So does it have to be 99% for it to be like powerful? Like the higher the percentage, like, so like a 99% confidence interval is larger than a 95%.
Yep.
So can you take more confidence in a bigger percentage than a small?
Yep. Yeah, you can be more confident in a 99% confidence interval than a 95% confidence interval. But the trade-off is that you have a bigger range.
Right.
So,
and then bias would affect the numbers, right? So like there's some bias involved that would come down.
Bias will just shift your everything, your point estimate, your lower and your upper limits. It'll shift all of them in one direction or the other. So this tells me that a lot of people here probably don't put enough of a difference between being 50% confident and 95% confident. A lot of you don't quite realize how much wider a range you probably have to be 95% confident in something. I mean, that's a hard thing to do. Definitely these 4 guesses down here don't, because they're in the wrong direction, but even these ones here, it just means that probably one or the other of those intervals is not well calibrated. Either your 50% confidence interval is too big or your 95% confidence interval is too small. Any questions? All right. All right, so we have spent a while already talking about the normal distribution and using the normal distribution to calculate some probabilities. But I want to introduce you now to the student's t-distribution. And it is useful for calculating confidence intervals and hypothesis tests when the sample is not so large and when the standard deviation is not known from the population. So the sampling distribution that we learned about when the population standard deviation was known, or it was a very large sample size, like more than 500 or something, we used a an assumption of a normal distribution for the sampling averages. But when we're estimating everything, the mean and the standard deviation, just from a small sample, that's where the student's t-distribution becomes useful. And it was originally developed by this person, William Gossett, for quality control of small batches of beer, when he noticed that the sampling variability among small numbers of batches was more than expected. So like the variability in the average properties, like the average alcohol content, from one small batch to another was more than he expected. They're calculated in the same way, though, in that to calculate a z-statistic, you took the sample mean minus a population mean and divided by the standard error. The only difference with the t-statistic is that the population standard deviation is unknown. So in this calculation, you're using S, which is the standard deviation estimated from a sample, instead of sigma, which was the population standard deviation that was somehow known. So this is actually a much more common situation where you're constructing a confidence interval or doing a hypothesis test, and all of your data come from the sample. So because we don't know in many situations the true population standard deviation, just like the average, we have to estimate it from the sample. We calculate the standard deviation using that estimate from the sample, that estimated standard deviation. Divide that by square root, and we get our estimate of the standard error. And then the difference is that when we calculate this t-test statistic, and we look at the sampling distribution of it, does anyone remember what a sampling distribution is? So remember that, like, say, with the infant birth weights, we all know what the birth weight of an infant is. It's how much an infant weighs when they're born. We have a sample. We can calculate the average birth weight of that sample. We repeat the sampling over and over. We get a different average for each one of those samples, and that distribution of the averages is the sampling distribution. So when we do a study, we just get to observe one average on the sampling distribution. But when we calculate this quantity, the sample mean minus some hypothesized mu0, or we could just say that's 0 and leave it out, divided by the standard error, where the standard deviation part is estimated from the sample. That sampling distribution, which was z-distributed before, is no longer z-distributed. It's another distribution that we call t. So this t-test statistic is calculated in the same way as a z-test statistic, except that its distribution is called the t, or the student's t-distribution. So Supposing that a statistically or a simple random sample of size n is drawn from a normal distribution, we're assuming that the population distribution of the individuals, like the individual birth weights, is normal. Then our one sample t statistic is the sample mean minus, it's in the we'll talk about in the next class about what this mu0 means. We don't actually have to know what this mu0 is. It's just a hypothesized value. So we don't have to know the population mean. But that divided by the sample standard deviation divided by the square root of n gives us the t statistic. And its distribution, if it were drawn from a normal distribution, is the t distribution with n minus 1 degrees of freedom. That's a new terminology for you. Degrees of freedom is essentially how much extra data that you have to calculate what you've just calculated. And for this particular statistic, it's simple. It's just n minus 1. So if we have a sample size of 206, then we have 205 degrees of freedom. Sample size of 17, we have 16 degrees of freedom. And there's a different t distribution for each number of degrees of freedom. But the density of it is symmetric about 0 and bell-shaped. So it looks a lot like a normal distribution. The difference is that the tails of it get kind of wider and fatter for fewer degrees of freedom. So for some smaller number of degrees of freedom, the distribution will be more spread out. And this kind of makes sense because when you look at this statistic, if this were instead sigma, which is always the same, then there's no variability in it. Whereas because we're now estimating x bar and s from the sample, there's going to be sampling variability in both of those things. So you're going to get more variability in t. It just has to be that way. Right? We're estimating 2 of the quantities in it instead of 1. So sometimes you'll, by chance, get a large x bar and a small s, and you'll get a really large t statistic. So that's why the tails, the smaller the sample size, the more the tails of this t distribution get spread out. And that sampling distribution has more variability in it. But that said, it's just another distribution, like the normal distribution. The only practical difference, if you're using tables, is that the way you look up probabilities in it is a little bit different. And you won't be able to look up the left probability for like any value of z like you could with the standard normal distribution, because it has to give you probabilities for a bunch of different degrees of freedom. So you will look up your number of degrees of freedom, and you can do it for every degree of freedom up to 35, 45, 50. So they give you lookups for any number of degrees of freedom up to 50, and after that it goes in increments of 10, then increments of 50 and 100. And they, rather than giving you a whole bunch of probabilities that you can look up, they only have a few of them. Let's see, there's a one-tail probability, which is just, say, the left side, or the right side, and a two-tail probability. So just looking at this one, a one-tail probability of 0.025 and a two-tail probability of 0.5, and they give you these, this is in your textbook, these nice pictures here to show you exactly what the probabilities are that you're looking up here. are given in the table. So do you remember that special number for the 95% confidence interval? How many standard deviations above and below the mean? 1.96? Yep. Well, if I go look, so here's two-tail probability of 0.05 and an infinite number of degrees of freedom. There it is, 1.96. But as we get fewer degrees of freedom, and it's notable even at 400 degrees of freedom, that critical value just keeps on getting larger. And down at 1 degree of freedom, it's 12.71. So that means that your confidence interval with only 1 degree of freedom, your 95% confidence interval is going to be like more than 6 times bigger, or your margin of error. And I noticed that that difference from between the standard normal distribution and the t-distribution is even more pointed the further out on the tails that you get. So for this 99% two-tail probability, it's the margin of error is plus or minus 2.58 standard deviations for the normal distribution, and it's 63 for the t-distribution. So the difference is even more important as you get further out into the tails. So like any rule of thumb or anything, like if I say, you know, if the sample size is 500, you could use the normal distribution no matter what. Well, that does depend on what probability you're looking at. If we were to go down to like a 99.9% confidence interval, even at 500, there's going to be more of a difference here. So for that reason, in practice, the software you use, if you're estimating standard deviation from a sample and you're making the assumption that it's from a normally distributed population, it's going to use the t-distribution no matter what. Because it is that sampling distribution of that t-statistic is t-distributed, whether you have few degrees of freedom or a lot of degrees of freedom. It's just that for a lot of degrees of freedom, it starts getting more and more similar to normal distribution. So, students' t-distribution depends on degrees of freedom, and your degrees of freedom for this statistic calculated from the sample is the number of independent observations minus the number of parameters estimated during the intermediate steps. So that sounds a little complicated, but for one sample, it's just your sample size minus 1. Or alternatively, if you know the value of the statistic, like the t-statistic, it's n minus the number of observations that could be recovered if lost. So if you knew the t-statistic, you could lose one of your observations and then figure it out again just by like guessing everything until you got the same t-statistic again. So, for a normally distributed population, we use the t procedures for confidence intervals, and we use it in this calculation of the margin of error, and we use it for hypothesis testing, although we don't get to hypothesis testing yet this class. For confidence intervals, you construct confidence interval by taking the sample mean plus or minus the critical value for the confidence that you want that interval to be for, times the standard error. For hypothesis testing, it's a little bit different. You calculate a value of t and ask whether that exceeds the critical value of t for a given type 1 error rate and degrees of freedom, which I think we'll just get to next class. So for example, the alcohol content of beer from 5 homebrewed batches. If I went and measured them from these 5 batches, got 5.5, 5.2, 5.7, 5.0, and 5.6%. And I wanted to know what is, for this procedure, what is the average alcohol content that it produces? What is the 95% confidence interval for that average alcohol content? So I want to know that, okay, I expect a little bit of variability, but I expect the average to be what it should be, like 5.5% or something like that. That would be the confidence interval approach. Or alternatively, is there evidence against the null hypothesis that the mean alcohol percentage is 5.0 at a confidence level or a type 1 error rate of 0.05? Those would be uses of the t distribution. These are the assumptions that we're making. First of all, that our data come from a statistically random sample. And second of all, that the population, so that individual measurements from the population are approximately normally distributed. 2 assumptions. However, these procedures are pretty robust. And what I mean by robust is that the outcome of it is not too sensitive to violations of those assumptions. And in particular, that assumption of normality is robust too. So if the real population, like of beer alcohol percentages and birth weights of anything is not precisely normally distributed, these 2-tailed t procedures are quite robust to that. And they're also conservative in that if there is some departure from that assumption of a normally distributed population, then your confidence intervals will tend to be larger than they need to be. So they lead you to make mistakes not often enough, or to cause you to be too conservative if the underlying assumption of a normally distributed population is violated. With one exception that one-sided tests do not work as well as 2-sided tests when the population is skewed. I don't think we're going to get into really one-sided tests in this course. That is tests where we're only interested in one tail of the probability distribution, so only interested in the uncertainty in one direction. Those tend not to work so well with departures from normality in the population. As a practical matter, if you have a sample size of less than 15, then your population should be pretty close to normally distributed, and otherwise you should use non-parametric alternatives. You don't always know if the population is normally distributed or not, but sometimes you can make a good guess based on other studies that have been done, or based on your knowledge of these types of data, like heights, weights, tend to be normally distributed. Incomes tend not to be. So you can, just based on knowledge of a certain kind of data, maybe make an educated guess about whether the population is normally distributed or not. If your population is normally distributed, then these t-based tests are very powerful. They're a very good choice, and they're much more powerful than these so-called non-parametric alternatives if the assumptions are in fact met. Non-parametric, something else we don't really get into in this course, but these are alternatives that make no assumptions about the population distribution. They tend to do that by replacing quantitative values with ranks. So you're only looking for differences in ranks, and it doesn't matter what the actual distribution of values is. But if the sample size is greater than 15 or greater, then these t-procedures are pretty safe, except in the presence of big outliers or a really strong skew. And if the sample size is greater than 30 or 40, then even clearly skewed distributions, you're not going to go too wrong with using t-procedures. You can also use your exploratory data analysis, histograms, box plots, dot plots, to investigate these properties from your sample. However, that other assumption that the data are a statistically random sample, that is always important, no matter what test you do. If it's not, using non-parametric tests is not going to help. These tests will not be conservative anymore. That is an important assumption, that every one of your observations is independent. If not, there are other more advanced methods for taking into account dependence among samples, but nothing that we'll get to cover in this course. So if you're going to use these procedures, those observations need to be independent. So, an example of violating that in this survey, like I mentioned, would be if there were groups of students all discussing their answers and then answering them. Those would not be independent answers. And that it's a statistically random sample, again, that, if it is not, really no statistical test can help you with that. Any inference about the population is going to require a statistically random sample from that population. So a little bit of Q&A here. When estimating standard deviation from the sample, instead of knowing it from the population, we use the t-distribution. Is that true or false? True. Very good. Is the 95% confidence interval larger or smaller when using the t-distribution than when using z? Sorry? Larger. Yeah. Yeah, because the tails of that distribution are larger. That sampling distribution will have more variability. As n increases, the t-based confidence interval becomes more similar to the z-based confidence interval. That's true. Yeah?
It says you use t when samples are large, like 30 to 40. So how large does it have to be before you get towards z?
So the decision between using t or using z is based on whether your standard deviation is estimated from the sample or the population. The standard deviation is estimated from a sample, then you use t, period. Doesn't matter what the sample size is. As we saw on this table, they become very, very similar for large sample size. But that doesn't mean you're substituting Z. It just means you get the same answer from both. The rules here that I gave you were about violations of this assumption of normality. So both the Z tests that we did before and the T tests from now, both of them rely on this assumption of a normally distributed population. So you could use these same guidelines whether you are estimating standard deviation from the sample and using T, or whether you know the standard deviation and you're using Z. You could still use these guidelines. All right, so let's, any uncertainties about these Q&As? Anyone not convinced by one of those answers? Did everyone get a chance to write down these answers? All right. So let's summarize confidence intervals. Confidence intervals give an interval that is likely to contain the true population mean, whether that be age, cholesterol level, professor's age, whatever, but it's the population mean. So it is an interval in which we have a certain specified level of confidence that the correct population mean lies. It is about uncertainty around that fixed but unknown population mean. And high confidence requires a larger margin of error, so wider confidence intervals. Your best point estimate from a sample is at the middle of that confidence interval. So we put the confidence interval at plus or minus the margin of error above and below the point estimate. Standard error and the confidence interval tell you nothing about variability in the population, only the uncertainty in your estimate of its mean. And that's an important misconception that you not make. That it's not telling you about like the percentage of individual birth weights in that range. It's telling you about your uncertainty about the population average infant birth weight. You use this T distribution anytime your standard deviation is estimated from the sample, but it becomes more and more important with small samples. Any questions before we wrap up?